Yeah, please, please.
We can start.
I request Professor Chandrasekhar to introduce today's speaker.
Okay. Yeah, it's a great pleasure to introduce my old student. Yeah, Dileep, I think joined for his MTech in 2004, if I'm correct.
Yes, yes.
Yeah. Then immediately after MTech, no, he joined for the PhD. Actually, before joining MTech here, he was working at a college called Nithe in near Mangalore. So after completing his PhD at IIT Madras, immediately joined IIT Mandi. I think it's in 2013, if I'm correct.
Yes, yes.
Yeah.
2013.
So he spent nearly 10 years there, and just last December he moved to IIT Harvard, and he's currently working as associate professor at Department of Computer Science and Engineering at IIT Harvard, and he also has taken over as the head of the department just about a month ago. Okay, and it's my really pleasure to say that Dileep has the best publication record among all my students. Two transactions papers, one paper in IEEE transactions on neural networks and learning systems, one paper in the IEEE transactions speech and audio processing, then another paper in a highly reputed journal speech communication. Besides that, he has a few papers in conferences like ICASP and InterSpeech, right? All of this is just out of his PhD work, right? And as I said, the best amongst all my nine students who got the- and he was also a TA for many of my courses when he was here, and we also jointly organized many uh, programs like Winter Speech on Winter School on Speech and Audio Processing when it was conducted at IIT Madras. He was very closely involved. Then, when we conducted this Interspeech conference in 2018 at Hyderabad, which is a large-scale international conference, he took a very active role in this conference. So he works very hard. He is highly dedicated and committed. And at IIT Mandri, he contributed a lot to the growth of the institute because when he went there, I think the institute was old by maybe a couple of years, right? So there were lots of activities that need to be taken care of. I think if I'm correct, he was in charge of all the networking activity in the
True.
IIT Mandi for several years,
Yes.
right? Until he left, I think he's been taking care of all the networking activities.
Right.
And he also introduced many courses related to data science when he was at IIT Mandi. Uh, and it's also a great pleasure to inform you that he has been selected for the Best Teacher Award at IIT Mandi, not once, but twice. Right? So it's really a pleasure to see that Dileep has been performing extraordinarily well as a faculty at IIT Mandi. He also handled many research projects. He guided the PhD students and a few MS students. So he has been very active in the field of mainly speech processing, machine learning, currently deep learning, and even some projects related to networks. So he's got a wide range of experience of doing research in several areas in computer science. So it's my pleasure to invite Lee to give this talk. Over to them.
Yeah. Thank you, sir. Yeah, it's really my pleasure to be here, and thanks for inviting and then having a discussion with you all. It looks like I'm back to the my my own student days. So yeah, looking into the IT Madras and then interacting with the CSC department. So thanks again. Thanks for the nice introduction also, sir. Yeah. So yeah, let me share my screen. So hope I'm audible clearly, right?
Yes, yes.
Hope there.
Yeah.
screen is visible, right?
Yes, the screen is visible. We would probably want to keep it in the presentation mode.
Yeah, right, right. Okay,
Yes,
so
perfect.
it's visible, right? Okay, all right. Okay, so yeah, what I'll do is that I'll just 30 35 minutes talk about one of the work on the spoken language identification, especially when we do it in the real world conditions. And then I'll share my journey from IIT Mandi, IIT Madras, which laid a good foundation in carving out my career in IIT Mandi and IIT Dharwad. So that's what I will try to do it in the later half of the things. So yeah, so the spoken language identification, as it says, the idea here is to basically, given the speech signal, identify what language a person has spoken. So that is what is called as the spoken language identification is concerned. So when we look into this spoken language identification, when we do this, so it should be independent of the person who has spoken and independent of what a person has spoken. That means it should be independent of the speaker and as well as the independent of the text with which a person has spoken. Okay, so that is the things involved in doing an automatic language identification in the from the speech signal. I'll straight away get into the problem of this spoken language identification. In the framework of the machine learning, when we see this problem of spoken language identification, we see it as a classification task. Basically, we'll try to classify a given speech signal into one of the language in which it has been spoken. So entire my talk, I will be focused on the situation that the speech signal is a monolingual one. That means the only one language in which a person has spoken. There are many other situations are there where this person can speak in multiple languages and other things. I am not at present in this talk. I will not be bringing that as a multilingual speech, the language identification cases. So only the monolingual language identification is I'll be considering here. And as a part of this classification task, the outcome of this task is basically the classes. So they are nothing but the identities of the languages. So which are in which which is embedded in that spoken in that signal. So typically in the framework of machine learning, when we see this task of classification, obviously it involves the two phases, the feature extraction phase and as well as the language classification phase, basically the classifier phase. So given the speech signal, so when we extract the features, the speech signal, if you see, it's a time varying signal. And for any language classifier pattern recognition model to be built, it requires what is called as the stationarity should be there in the signal. But speech is a continuous time varying signal. The stationarity will not be available from the entire speech signal, but it will be found only in the very short segments of the speech of around 20 to 30 milliseconds. That's why the speech signals are called as quasi-stationary signals. And when we extract the features, we do a kind of a short-term spectral analysis on the short segments or short frames of 20 to 30 milliseconds, and we extract various features, typically the features like Mel frequency capture coefficients, Mel filter bank energy coefficients, perceptual leader prediction. These are some of the features which we extract from that sequence of feature vectors. Okay, and these are not the only the features which we extract. These are some kind of a features which are computed or extracted from this signal, and sometimes we also learn some with respect to some task specific cases. We learn some informations associated to that particular signal, and we embed them in these frames from where these features are extracted. Typically, for this language identification cases, so the 20 millisecond frame will not actually represent the language that is present over there. Usually, a larger segment of the speech is used to represent a kind of an identity of the language that's present over there. Because for languages to differ from one language to another, so the phonetics and phonotactic informations are very important. They usually span in the larger time duration. So usually what we do is that we take some chunk of the frames and we make it as a kind of a super frame representation, and we try to learn some phonetic based informations or phone states to be embedded on them. So we typically learn it from some task specific pre-trained models. So some of them are like the phone state based bottleneck features, or in the recent days the wave to wake representation. So all these things are pretty much standard in recent days for representing the frame level features. So in recent days, even the larger segments of the speech, we embed what is called as the utterance level embeddings, and these are also the learned features which we represent them. Once we have the features which are represented, which are computed, or using the learning based feature representation, we take it. So we use it for the language classifier to classify that utterance to which class it belongs to. So typically, the kind of a the scenario when you see that, so the since the features are extracted from the short segments, whether it may be a learned features or it may be from the computed features like the ML frequency capture coefficients. So it makes your entire speech signal as a sequence of feature vectors. But when you look into the utterance, depending upon what a person spoke or how long a particular utterance has been spoken by a person, so that the duration of the speech signals are varying. As the duration varies, the number of feature vectors in that sequence also varies. That's where it leads to what is called as the varying length patterns. So when we try to classify a speech signal, we need to address the issue of classifying these varying length patterns. So conventionally, we use the statistical approaches like like the Bayes classifier using the Gaussian mixture model to model each of the utterances associated with each of the classes, and we used to classify them. So in the recent days, the deep neural networks are taken over by these the statistical approaches have been taken over by the deep neural network. So there, the deep networks or deep neural networks, different techniques have been used to model and represent the features and as well as to classify the feature vectors. All right. So typically the frame level features like either the mel frequency capsule coefficients or the phone state based features from the bottleneck features or from the wave to wake representations extracted from some pre-trained DNNs. These are typically used to represent the frame level features of this speech signal, and so these are all in the form of the varying length pattern representation they will be there. So they are the inputs to my the classifiers to classify them into the classes. So current day state of the art the language identification system. So typically they are all based on the deep neural network based techniques. So as these deep neural network based techniques, there even though the inputs are given by these mel frequency capsule coefficients, which are computed, the features computed from the short segments of the speech signal. So internally, it has the two phases. So it not only learns the classifier, it also tries to learn the features which will be more specific to the language identification. That means the language ID specific features will be learned along with the learning the classifiers to classify into the classes. Okay. So typically here the frame level feature vectors are followed by the utterance level embedding extractor and then the classifier. So this is the typical framework or the pipeline in the current day the language identification system. So when you say this utterance level embedding, so this is where I was talking about the feature extractor followed by the language classifier. So both are learned to in the process of the learning the classifiers. Okay, so the in the state of the art system, the utterance level representation. When I say utterance level representation, so though the speech signal is represented as the sequence of frame level features, they somehow they will be combined to form a one utterance, one vector representation, which represents entirely one utterances. That's why we call it as an utterance level representation. X vector representation is the current day standard of the utterance level representation. So in this case, so this utterance level representation It takes the input as the sequence of frame level features. It may be either the X vector, either the BNF vectors or the MFCC feature vectors, or it may be a sequence of the wave-to-wake representations. So they are given to the input to the time delay neural networks, and they are followed by the what is called as the pooling layer. So in the time delay neural network, basically a chunk of the frame level feature vectors are given to the time delay neural networks. These chunks forms some sort of a take some kind of a fixed context of the speech signal. The roughly the chunks of the feature vectors they represents they usually at the subword level or the word level context in the speech. So which typically represents kind of a the language embeddings what can be possibly present over there. So that chunk is passed on to the time delay neural networks, and they combine to form what is called as the a higher context level representation, an abstract representation, which is called as the LIDC nodes. Since the sequence of such chunks have been given to the inputs, so the outcome of the time delay neural network will be a sequence of LIDC nodes, which are the intermediate representations. Each of these LIDC nodes, they represents a kind of the time context in the speech signal. It represents a hardly it's around word or subword level information will be embedded, or it represents in the time scale or the temporal context. Okay, and these LIDC nodes are passed to the utterance level embedding. That's nothing but a kind of a what we call it as a pooling layer. So where we do what is called as the statistics pooling layer. So statistic pooling means so from all this sequence of LIDC nodes, we compute the mean and the standard deviations, and this mean and the standard deviations are concatenated to form a one large super vector, and that vector we call it as a the X vector, or it's a utterance level representation. And this is the state of the art, the represent utterance level representation, which typically it is been learned in the current day language identification system. Okay, so if you look into that, this utterance level representation X vector is given as to the our fully connected classifier. So important things to understand here is that this utterance level representation is learned along with learning the uh, uh, learning the classifier. It's basically it's an end-to-end model. So in a way, we can see that this X vector embed the language ID related specific information. So more discriminative information it learns, and then that makes the language classifier more discriminative in classifying the language. So, motivated by this success of this basic X vector architecture, there are several variants of this being proposed in the literature. So, even we also proposed one such variant to that, and that approach, what we call it as a instead of X vector, we call that as U vector in order to differentiate ourselves from the X vector representation. So, the two major changes what we have done in this particular case, one of the change is related to this. Instead of the time delay neural network, we included the what is called as the bidirectional LSTM in order to consider kind of a sequence information present within a chunk of the feature vector, frame level feature vector, which are taken as an input to that. And with that, we represent what is called as the abstract level representation, what is called as the LID sequential signal. And the second change, what we have, second things what we have proposed here is instead of the statistical pooling of this abstract level representation, which is the LID sequential synonyms, so we used what is called as the self-attention based network to weighted summation of the LID signals in order to get the utterance level representation. So what we observed is that so instead of simply doing the statistical pooling, the self-attention based pooling where it gives more weightage to some of the abstract representations, so which are more relevant for that particular language to classify, and that is we expect that it should work better in classifying the language or the learning the more discriminative feature in that embedding in that utterance level representation. This is what our utterance level embedding what we have proposed in one of our earlier work, and then that is what we consider as a kind of a state of the art for all the recent works what we are doing it on the language identification cases. As I mentioned, this obtaining this the LID sequential synonyms and the utterance level representation. We call it as a U vector. So this is done in using the end-to-end LID network, and these features are learned along with learning the classifiers. Okay, so this is the standard which we are following as a basic for the language identification is concerned. Okay, but there are a lot of advancement happened in the in the recent days by the machine learning and in the deep learning environment. So the kind of a accuracy what we get in this the language identification, what we observe is closely 80 to 90% is easily we are getting the accuracies with respect to that. But in spite of all these advancements, significant advancements, so there are a lot of challenges still that exist in the performing the language identification. This challenge comes from when we look into the classifying this or identifying the languages in the real world conditions. Okay, so the main challenges are one is high intra-class similarities, the second is this what's called as the intra-class variations. And third one is the, which is most important things, which we will be focusing more on this presentation also. It is a domain mismatch between your training and the test samples. The first challenge when we say this high intra-class similarities, so this is quite common in any two of the languages which are coming from the same family. For example, if you consider these Dravidian languages, the Kannada and Tamil, or Kannada, Tamil, and Telugu, in all these cases, some of the typical phoneme sets or the phonotactics, or even some of the words sets are almost same in all these languages. So in that case, for example, simple case is in the word is called as the Amma, which is quite common in all Kannada, Tamil and Telugu and Malayalam. In all these cases, so it's like that there are many such things which are having a lot of common things across the some of the languages. So this gives us some kind of an high intra-class similarities. So that needs to be addressed. That is one of the challenge to be handled. That's one thing. The second thing is that it is with respect to what is called as the intra-class variation within the same language. So there are a lot of variations that should be there. These variations, intra-class variations, that's coming because of the dialectual changes and because of the accents in which the person can speak of a particular language. Okay, this is another serious challenge in the real world scenario, especially for the Indian languages to handle that. Okay, and apart from that, what we have is the domain mismatch. This domain mismatch, it refers to the differences in the background conditions in which the speech signals have been recorded. Okay, so the speech signal could have been recorded in it might have been recorded through the microphone, or it might have been recorded in a very clean environment, in a studio environment, or it might have been recorded through the telephone channel, or it could have been recorded from the mobile channel. And the important thing is that encoding that is used in all these different conditions, different channels, is different. And it is surprising to see that if you build a model using recorded in one channel, and then if you test it using another channel, the performance is very degradable. Okay, and apart from that, the same language might have been spoken by the multiple speakers. That's again the multiple mismatches, different way of speaking that will be there. And most importantly, type of the speech which will be recorded, signals which are recorded, so they might be of the read speech. For example, if you recorded the speech from the people who are reading from the paper, or reading the newsreaders the speech, if you have recorded it, and that is what is called the read speech. Okay, but if you record the speech like spontaneous or conversational speech, when the two persons are conversing, or the one person is conversing thing, so that is what's conversational speech. And both these cases, the type of speech when varies. So again, there's a huge mismatch that will be there if you build a model using one type of the speech, and then if you try to test it from the another speech type. And apart from that, noise and background, all these things makes the life of the identification is very miserable. Okay, so this is quite common. These all these things are quite common in the real world condition. So in the entire my this talk, in this particular talk, in the next few minutes, so I will be focusing mainly onto the how one can handle this domain mismatch condition, and what could be a possible solution. It's a difficult situation, but still, what could be a possible situation, or one can solution one can do for this. This is what I will be focusing on the next couple of things, and then one of the recent work which we have done, I'll just discuss that, and then I'll wind up the things. Okay, so because of all these things, even the state of the art LID systems, which I just shown with respect to X vector based network or the U vector based networks, they perform they unsatisfactorily in this real world condition. So one thing how to improve this performance in these conditions. To answer that questions, one thing is that to get that satisfactory performance in that real world condition, so one thing is that your LID system that needs to be generalized. It should be generalized well to all the different background conditions. So improving this generalization, it always helps to handle the challenges, all these challenges of domain mismatch or intraclass similarities or the intraclass variations. The handling these intraclass similarities and intraclass variations are a little harder, and that needs some different approaches to follow that. But what I'm concentrating on that is only onto the domain mismatch conditions. So domain for me is the change in the background conditions in which the recorded speech are coming from. Okay, so that is where I am focusing on for the rest of the talk. Okay, one of the simple way to handle for this is that to improve this generalization is that so the you train the model by using the large data set with the variety of background conditions. So you anticipate all possible background conditions, collect the speech signals from all those different background conditions, and build the models. So change different large number of speakers, large number of variations of the channels and the different environments, and then build the model. When you do that, they usually it's going to address these issues of variations in the domain mismatch, and when these techniques have been used, so it works well on any of these background condition changes. But however, to do that, we need to have huge data set from all possible backgrounds things. Getting such a huge data set requires a lot of human effort and a lot of money that involved in that. So in the especially when it looks into the trying to use the identifying the languages which are typically we call it as a the low resources languages, typically all the Indian languages. So we do not have enough samples for each of the languages. Okay, and the collecting all possible such changes, variations, those background conditions, it's really hard to get that. So the now my question is to under in such under resource languages, if you want to do a robust identification of the languages to perform, so if we are not able to collect all possible variations in the background conditions, then what would be the alternate solution to address that? So this is where we wanted to work on, and this is where we are working on one of the topic, right? So this non, so that's where, so we are not the only people who are working in addressing the solution for this. There are many techniques have been proposed in the literature. So some of the things, basically, the idea is to come up with some kind of a different sophisticated training strategy so that this so that we can get some sort of a generalized model. It should be agnostic to the changes in the variations in the channel in which the recording has been happened. So that's the goal here. Okay, there are certain tasks like the supervised or unsupervised domain adaptation. This is one of the few techniques that is available. So where we try to adapt the languages or the sorry adapt the speech signals to the different domains from where it has been collected, and then to make it slightly generalizable in the condition in which it will be used. Another thing is that what is called as the adversarial multitask learning. It's also one of the very the popular techniques that's used to improve the domain invariance cases. But only the limitations of these two things is that, so in order to perform this domain adaptations or this adversarial multitask learning, a priori we need to know the what is the target domain from where these things are coming from. Okay, that is slightly a downside of these things. If I know that okay, these are the different domains from where it will be coming, so even though we have the very limited samples, so I can adapt these things and I can get a better performance for when I was trying to test from any of the domains is coming to it. But there are many conditions, especially for the Indian conditions and especially for the real world scenario. We do not know from what target domain the my test samples are coming from, right? This is what I call it as unseen target domain. In such scenario, all these techniques will fail. Okay, so this is where we are trying to find a solution to see that can we come up with some solution so that some way we can adapt or some way we can address this the unseen target domain cases, and can we perform some better approach here. All right. So before going into the what is our idea and the goal with which we have went into, let us try to see with some experimental studies to see that effect of the changes in the channel or the domain when we are trying to test the language identification system. So for that, we have used the two data sets here. One is the what we have collected as a part of the bigger consortium project. We are involved with that. I will just discuss that at the end of the presentation. So we have collected as a part of the project is what is called as the IIT Mandi Indian language data sets. It has two parts we are having. So one is the red speech data set, because we have collected those red speech data sets from the All India Radio speech corpus. So almost like we are targeted for the 8 Indian languages, which is listed here. Almost like approximately 4.5 hours of speech utterances have been considered for each of the languages, and there's a sufficient speaker diversity which has been considered in that. And this is what is we call it as the red speech, because it's collected from the All India Radio news readers data which has been collected. So typically they read the speech, read the content, and the speech is what we call it as a red speech. So we have almost divided that in the training set and the validation set here. So both are coming from same domain in which the recording has happened here. And the second data set here in the same set is what is called as the YouTube data set, which we have taken it from the different domains, the different domains from the in the different sites from the YouTube. So most of the speech signals or speech utterances in the YouTube dataset, which we consider are not the red speech. They are mostly they are the conversational speech, and we do not know that from where or what kind of a channel in which they have been recorded. Whether it could be a microphone, it could be a microphone, but the channel variations and the background variations are totally unknown to us in this case. And we consider this YouTube dataset only for testing the model which is trained using the red speech data. So this is what we'll be seeing that. Okay. So for our apart from that, this is on Indian languages cases, just to be in line with the what the world is working with. So we also considered, we also participated in one of the challenge. It is called AP OLR challenge. So this is consists of around 10 languages from the OLR what is that? Oriental languages data set, including Russian, Japanese, Vietnamese, and all this Oriental languages as a part of those things. So here there's a particular challenge or the task here is the cross-channel LID. So where the training and validation sets are coming from the one set of channel information. So we do not know what channel they are actually, and but the test set is completely they carefully they have collected from the totally the different channel which is not seen during the which is not there in the training and validation set. And this is the challenge to address that, how it needs to be addressed, this needs to be the handle kind of a thing. All right. So this is the two data sets we have used. So for our experimental studies, so we have the two type of the test sets. So one test set, what we call it as a scene test. Here the scene test in the sense, it is not the scene with respect to the test set is not seen. It's not that they are seen during the training case, but the domain information, domain conditions are seen during the building the language, the system or the training phase. That means that the channel conditions or the background conditions are same for both the training set as well as for the test set. Okay, so in this particular case, when the each of the data set has the respective validation set, which acts as a scene test for that case. The second thing is an unseen test. So in this particular case, the domain conditions are totally unseen. by the system while doing the training case. For the system which is trained using the red speech dataset, the YouTube dataset is acts as a unseen dataset because its channel conditions are totally different than that. And in the APOLR dataset, so there's a cross-channel test set which is dedicatedly it has been used for testing such unseen test set. Okay, these are the two test conditions which are having there. First, if you look into the how this state-of-the-art techniques are they're performing on the seeing test set. If you look into that X vector net and also the U vector net, what we have proposed by motivated by that X vector cases, you can see that almost the 92 to 94% of with that accuracy, the language identification happens when the both the training and test domain conditions are same, channel conditions are same. The same is the case with respect to the APOL data sets also. But when you see the test with the cross channel or unseen test condition, so if you see that when the model has been trained using the red speech dataset and it has been tested by the YouTube dataset, you can see that the accuracy has been greatly deteriorated to 60%, 60 to 64% in both the cases, right? And even in case of the APOLR cases, that cross-channel test when we do that, went down to the 68 to 71% in both those cases. So this is what is I was talking about. That is the real conditions when you do not have the sufficient samples to build the model, and we have built the model using only one set of background conditions. When the background condition changes when we are testing it, okay, so this is where it tries to the performance tutorial. This is quite natural that when we want to build any of the speech related system that is put to use by the user, okay, if you want to do an ASR or the thing, so first you need to identify what language it has to be done. The built model is using the data set coming from some domain, and your utterances when you are put to use in a real world condition, so the performance deteriorates like anything. So this is what is the scenario what I was talking about. So now the kind of an attempt what we have made to address this is that, so the objective is to basically to improve this robustness of this LID system in the real world condition when the training data set contains a very limited diversity. Okay, that is what I was talking. Channel conditions are unknown to us. So specifically, our objective is to learn the embedding, the utterance level embedding. What for us it is a U vector learning, such that it should efficiently encode the language ID specific information, in spite of they are coming from the different domain conditions. Okay, so that is the major objective here. Okay, so in order to address this, what we are trying to follow is the what is called as the bi-resolution processing of the speech. So this is what the idea we follow that. So with that, what we are trying to do here is that, so we have the utterance level embedding extractor, what the U vector utterance level embedding extractor is there. So instead of, so now the idea what we are using here is that, so if you consider the speech, so now the speech is a combination of both the speech component, foreground speech component, and also the its background component, which is maybe a channel or the speaker informations or the any noise or that things. So it is a combination of both speech as well as the background information. But if you take a speech utterance, the idea is simple. So if you take a speech utterance over the period of time, what is fastly changing is the speech content is fastly changing. Okay, it is a changing with respect to the time. But if you look into the entire utterance, if it is spoken by one speaker or if it is recorded by a microphone, its channel information will be almost the constant throughout the entire speech utterance. Okay, so this is what we are trying to exploit on, right? So it's trying to, as I was telling, it's a fast changing speech component, and also we have this slow varying or the almost a constant component of the channel variations that is going. So what we try to do here is that, suppose if I process the same speech signal with the different time resolutions, when I say the time resolution, we extract the features from for every 20 millisecond frame with the shift of 10 milliseconds. So like that, we extract the speech signals. That's how the processing, the sequential processing of the speech signals happens. Okay, now instead of doing that, that's a one way of doing it. At the same time, instead of doing the 10 seconds of 10 milliseconds of frame shift. Let me change frame shift of the 20 milliseconds or the 30 milliseconds frame shift. Okay, so by that when we process it, so I will have the same speech signal processed by using the two different utterance, two different temporal resolutions. Okay, now if I pass this two different temporal resolution to their respective utterance level representations, I'll get a U vector representation from both these temporal resolutions. Okay, now if you take this case, so now what has happens here is that both these two utterance level representations, which are coming from the same speech signal, will have some sort of a complementary informations with respect to the speech is concerned, because we are changing the temporal resolution of the speech. But among them, what is common in among both these embedded embedded representation is that, so that will be the channel representation or the background condition is almost the constant in both the cases. All right. So now when you put this in the our end-to-end model to learn this representation, okay, so what we believe is that it tries to learn the language ID specific informations more rigorously than the which is commonly the channel information which is common across the space signal. Okay, that is what is represented in this particular figure. So now given a speech signal, so the frame level feature extractions with the different temporal resolutions is passed through the embedded extractor. This is same old the U vector representation pipeline, and then this is also the different time resolution. So it is passed through the embedded extractor too. So we get the two embeddings E1 and E2. They are the two U vectors, we can say that. And then by using the self-attention based model here, we try to combine these two utterances. This combined utterances will have the more emphasis will be on the dissimilarity among those things will be the speech content, but what is common among both the things is the channel variations that is present with respect to that, and that is given to my classifier here. So since it's an end-to-end model, when we learn this utterance level representation U vector now, so this will have more discriminative information with respect to the language ID than the channel ID cases. All right. So we will be minimizing what is called as the cross entropy loss in the process of doing the things. So when the U vector, the utterance level representation is learned, it learned by performing this by resolution processing. All right. So this is the idea which we have tried to address this thing. All right. But in this particular case, so what is one thing missing here is that, so our intuition is that by doing this case, so the dissimilar informations about the speech, okay, that is should be emphasized, but the similar informations about the domain specific contents, so that is common across both the things, that should be suppressed. But we are not doing any what is any explicitly performing any kind of a suppression of this what is called as the domain specific information, which is common across both the utterances here, both the utterance level representations here of the same speech signal. So what we have, what we also proposed in this particular case is that we try to, we need to do some kind of an explicitly encourage this embedding extractor to suppress this common domain specific utterances when we combine these two utterances. Okay, so for that, so we propose what is called as the within sample similarity loss, so which encourages the network to suppress the domain specific contents. This within with WSSL or the within sample similarity loss, it is nothing but a simple cosine similarity between the two embeddings which are coming from the two branches of embedding extractors. Okay, so when we compute the similarity, so this if channel conditions are since the same with both the things, so the similarity should be the higher with respect to that. Okay, so now when we are trying to put it in the loss function of my classifier, so now the loss function is not only the cross entropy loss, which is the classification, it is loss with respect to the loss which we are minimizing with respect to the language target, okay, we are also trying to minimize what is called as the within sample similarity loss between the two utterances. Okay, so by this, when we are minimizing the similarity, that means that we are trying to suppress that uh, 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 the the common information that is present in the within the utterances which are learned in the embedding extractor. Okay, which what is the common information, that is the channel information present in the two utterances, sorry, the embedded utterance level embeddings coming from the two branches of the same for the same speech signal. And we are minimizing the loss of classification loss, means we are trying to that helps us to incorporate more and more discriminative informations into, will be embedded into the final combined embedding is concerned. Okay, so this is what is the setup which we have included here, and this is what we try to see that for some extent it should suppress the channel conditions. So in it, irrespective whether it has been this is what happens during the training cases. When the training case, it learns this embedding extractor. During the test phase, again when we pass the test example, which may be coming from the different channel informations, so again the bi-level processing, by resolution processing happens there. So when the bilateral processing happens there, when and during the when it combines here by using the self-attention based model, so since it is already learned to minimize the common information between the two utterances, two representations of the same utterance, so what is suppressed is the channel information which is common in the two utterances here. Okay, that is what is we believe, and that is what is the intuition with which we work with respect to this. And it's surprised, it is interesting to see that that when we repeated the same experimentation with our proposed WSSL based network, so for the same test set, which is the test conditions are the same as that of the training set conditions, you can see that. So though the WSSL based network, so this performed significantly better than the other state of the art LID systems. So even though the channel conditions in both test and training are the same cases, that means that the proposed approach is learning the discriminative information with respect to the language ID. It is learning very well. That is the one thing. Now, when it is been tested onto the unseen conditions, so for the model which is trained using the red speech and then tested using the YouTube cases, so there is a significant improvement in the performance we have seen. Though it is not gone up to the something like an 80 or 90% of the accuracy, but from the 60 to 64 to the 74%, this is what we believe which is a very significant thing. Okay, and at the same time in the APOLR challenges, it also has a very significant improvement we obtained using the technique which we have proposed. All right, so there are few reasons why in the Indian language conditions it has been not working here, is that the YouTube, not only the data set is not only having the channel variations, it also has a lot of linguistic variations in terms of the dialects and other things, which we have not taken care of during the training phase. Okay, so that is the one of the things which has been slipped off. And even in case of the APOLR challenges also, so in that also cross channel cases also, the channel variations have been very well been handled in this case. But this has been also has a lot of variations in the dialectual and intra-class variations or inter-class similarities, which I was talking about that, right? So those things are still that is there. Okay, but in the context of the cross-channel cases we consider, this is our approach is really promising to look into the look ahead and then see the things. And in case of the APOLR challenges, when we approach the challenge, so it's almost the last day of the things we have submitted our results. So at that time, without much training of the model itself, we have reached around fifth place in the thing. But after the challenge is over, when we refined model, when we have tested with their test model, so we beat all the system which has been proposed during that particular challenge. But unfortunately, we could not participate with the full model on time. So that is the thing. But we have a satisfaction that okay, so this approach is really promising in that direction. Okay, so this is what I wanted to highlight or need to discuss as the one of the challenge what we were doing in the spoken language identifications, typically in case of the current day standard, is that to address the spoken language identification, typically in the domain mismatch condition, because this is the one which we have considered that one of the serious challenge when we're taking our language recognition systems or any of the speech recognition system to the market, and when it kept in use it for the public. So the channel conditions or the recording conditions changes, so that has a serious effect in the case. Okay, and this is one such approach showing a kind of a promise to go ahead and then perform the things. Okay, so we propose what is called as the bi-resolution processing of the thing. There are a lot of variations one can bring in here. We also have done a lot of work going ahead with the things here is that when we one of the thing is that when we have the bi-resolution things, there is we also observe that there's kind of an imbalance in the learning between the two branches over there. So we also proposed an approach to balance the learning between the two branches of the by resolution processing thing. And at the same time, in the recent things which we have replaced the what is that? The bidirectional LSTMs in the address level representation, right? So we have replaced it with the transformers, which also shown a more very promising, and then it's outperformed the performance, our own performance using this bidirectional LSTM based address representations. Okay, so these are some of the advancements which we have done in these cases, which is the one what I wanted to discuss in this case. So I'll stop for here for some questions. Any doubts or any questions associated to this, or maybe I'll take a couple of minutes just to see that apart from this work on the what I'm saying, the speech related work. So I also working in the other allied areas where the machine learning is the common thing over there. So my core research area is in the applied machine learning, but the three verticals in which I'm working is on machine learning for the computer vision, the cloud and networks, and it's the speech and audio cases. So the speech and audio cases, as I already mentioned, the kind of given the idea for some of the work. So that's the spoken language identification is the key things which I was working on, specifically coming up with the robust utterance level representation for the real world condition. Apart from that, so for the multilingual speech conditions, so when a person's speech, it's a typical happens in when we speak in our vernacular language, that our when we speak in our own vernacular language, so we typically code switch with respect to the English. Okay, so there the identifying the language, whether it's the Kannada or it's a English, and where the change of the language happens, this is what is called the spoken language diarization. This is another direction I was working on that. And of course, we also work on that what is called as the dialect identification. And with respect to the dialect identification, can we address the issue of along with identifying the language? So the identifying the dialects, which also helps in making this the robust identification case. Okay, so these things these works, or we are actively participating in the one of the sponsored project from the NATI, which is the Speech Technologies for Indian Languages. So this is under the NLTM and Bhashini project. This is a big consortium project where IIT Madras, Professor Hemamurthy and Umesh sir is leading this thing. So in that consortium project, my responsibility is to come up with the robust language identification system, which sits on the different speech technologies, where it may be an ASR or it may be the speaker recognition. So identifying the languages that helps us to go for the switching to the different speech related activities. So that is where this work is heading towards. And apart from that, in the computer vision domain, there are various works which I was working on. So one thing what I was earlier starting from my PhD work, where I prominently worked on the SVMs and then and designing the kernels for the length patterns. So we started with that for the various things, and then typically we went towards the learning some kind of a semantic based representation learning for the specifically for the scene images and the image classification cases. And recent days has been working extensively on the agricultural domain, where specifically from the images and the videos identifying the leaves, and from the leaves identifying the diseases from the things, especially in the real world scenario in the wild, detecting the diseases and the predictions from the leaves. So this is one of the area where I was working. And another one which I was working with in IIT Madras, or say IIT Mandi, it was that it's an ecological object detection, basically the animals and bird detection, their recognition from the camera trap sequences. In this case, it's a very from the camera trap sequences, first identify which are the frames in which these ecological objects are present. That's what we call the empty frame removal, we call that. And then from that, you localize the animals or the birds and then recognize them. So this is the different pipeline which we were working on. This is another direction which we were working on. And from the cloud and the networks, this is I'm really fortunate in IIT Mandi because of the professor tag and because of the responsibility of becoming an IT and infrastructure head. So I had to work on specifically coming up with the kind of a what is called as the predictive analytics in the network domain, specifically in the anomaly detection and the resource provisioning in the cloud data centers as well as in the telecom network. So the coming up with using the data analytics, coming up with the next generation the network management system for the telecom network, which is one of the valuable the project which we handled. It's the multi-crore project which we handled as a part of the Uchatar Avishkar Yojana from the MHRD. So this is the another vertical where I'm working on. Altogether, my major work is building on the algorithms for solving the problems using the machine learning. Right now, these are the three things. Apart from that, there are many various other areas, even in the interdisciplinary areas of mechanical department and civil problems, where we are applying the machine learning and then solving certain problems. This is where my research things have been heading towards. Okay, so maybe I'll stop at this point, and I'll be happy to listen to any of the questions or any other things associated to that. Yeah, any questions or any queries?
Hi, Dileep.
Yeah, yes,
Oh, was there a question from Professor Chandrasekhar?
No,
yeah,
no, no, no. I just
okay,
respond. That's all.
okay.
Hi, nice meeting you. I think we met at Monday, and after that, it has been a long time.
Yeah, yes, yes, that's true.
Nice to see you.
Yeah, yeah.
I, from someone who is outside the speech community, I mean, I
Okay.
was just, thanks for such an impressive talk. I think the
Yeah,
bandwidth of your work and all is, I mean,
yes,
uh, yeah, it has always been great and it continues to be great.
yes,
So one issue which I have, I think, as an outsider to speech in general, and also as a concern I have, which I think now that you are teaching students, you would also have.
yes.
I don't know whether it is relevant to the current discussion, but in general, it may be also.
Okay.
So when you're talking about language identification, for example, right?
Yeah.
So a large part of it is essentially looking at discriminative models,
Yes.
right?
Right. Right.
But if you really look at language identification
Yeah.
as humans do it,
Yeah.
right? So, what is your mother tongue? Kannada, is it, or
Yes. Yes. Kannada. More specifically, it is Tulu. Yeah. Yeah.
is?
It's Tulu.
Oh, okay, okay. I don't
Yeah,
know.
it's in the coastal Karnataka. This thing. Yeah. You can.
Okay, okay. So let's say Kannada or
Yeah.
Tulu or whatever.
Yeah.
So I mean, one is discriminative approach. If I hear a large number of people speaking
Yeah.
Kannada,
Yeah.
then I can essentially make a distinction between Kannada and Tamil and so
Yes.
on. even if I don't know Tamil or even if I don't know Kannada, which
Yeah.
is the reality,
True. True.
right? So this is the discriminative approach. I just get a
Yeah.
large number of data points
Correct.
and can be effective in
Yeah.
discriminating between the two languages, but I'm actually not able to speak any of these languages,
Yeah.
right? Meaningfully.
True.
But if I take a generative approach, then that would require me to actually know the languages,
Yeah.
right? And actually be able to
Yes.
converse. I mean,
True. True.
and that is the essential idea of discriminative, though in class, mostly only the equations are taught. So students hardly understand
Right.
the actual intuition behind why these approaches are there, actually, which is a major concern when you are teaching students. I mean, I don't know
Yes.
how they manage with that, but somehow it's very hard to get across this. So essentially, what one needs to understand is that we are saying that with large number of large data points, we are not getting improvements and all that,
Yeah.
but we never were perhaps supposed to get improvements, right? Because the generative structure was never ever there,
Yeah.
right? It was only looking at data points, and it was only trying to induce models from data points,
Yeah.
and
Right.
that's perhaps as best as you can do without a generative structure,
Hmm.
right? I
Hmm.
see a very disconcerting trend that people have dismantled the large category of AI techniques which used to exist,
Hmm.
not just classical AI, which
Yeah.
obviously many people
Yes.
don't know, but also
Correct.
statistical AI as it used to
Yes.
exist.
Right.
For example,
Correct.
Bayesian models.
Right.
Bayesian models are particularly effective with small data, right?
Exactly.
And
True. I
one
totally
of the
agree.
reasons is that it has a strong generative flavor that allows you to
Yes.
essentially
Yes.
encode rich models
Yes.
about how the data could have been
True.
generated.
Right.
And if you have really large amounts of data, you can train very
True.
sophisticated
True.
models with
True.
it.
True.
But I think this end-to-end game,
Yeah.
which is a very, very dangerous way of looking at the world, I would say,
Okay.
end to end. I think
So.
that's killing the party. I think.
Yeah.
I mean,
No.
what
No.
what I what I'm essentially concerned about. Let me
Right.
just complete so that I can express myself.
Yes. Yes.
See, suppose I just take physics.
Yeah.
If I just say end to end, then I don't really need the Newton's models. I don't need any of physics actually.
Yes.
I just need to observe, in fact, I mean, large number of data points of each individual throw of a
Hmm.
ball, each individual, and just see what is the input and what is the output, and then expect to learn
Yeah.
the models of physics like Newton's models and
Hmm.
Maxwell's models from that. I
Yeah.
mean, this is as stupid as that. I
Yeah.
mean, so basically, you can dismantle all of physics, you can dismantle all of linguistics. So
Yeah.
from class 1 to class 10, you don't need to study,
Yeah.
impart any grammar,
Yes.
because your idea is end to end. Even without learning grammar, in
Yeah.
slums, people can
Yes.
are effective in dealing with language. So you don't need anything. Actually, in speech, the thing is a little more effective, I think, because in speech you are less concerned about meaning, and it's not surprising that deep learning actually works better for speech than in language. But
Right.
even in language, people are saying Chat GPT, and they
Yeah.
don't understand what they're actually expecting out of Chat GPT. I mean,
Right.
this is kind of uh, I don't know. I mean, where it is leading. Sorry, I mean, I just kind of barged into it, but
Yeah.
it's
No, no, actually, yeah, you're totally, I agree with you. So, because, see, the one thing is that when we use these things in end-to-end in the speech, especially in this condition, we are not using it blindly. Okay, so because as one thing you said that when you hear the Kannada or when you hear the Tamil, so there's some sort of a difference you hear it, right? So this is where linguistically the people say it's phonetically they are different, right? The phone states of the data when we model that. So usually we use it using earlier using the HMMs and other statistical model we used to model this phone state models, right? So if we can embed these informations in our frame level features, and with that we go for an end-to-end model. So this is where the things will change. Okay, so because
yeah,
if
yeah.
you
But Dileep,
one
I mean,
thing
what? Yeah,
one thing I have not given much details about the what speech part has gone ahead in this machine learning cases. So one thing is that our frame level features when I was talking about, right? So I'm not just using only the MFCC feature vectors. So I'm trying to embed the phone state information which is coming from some bottleneck network which is trained to detect the phonetic informations associated to it. I use that pre-trained model to embed these phonetic informations into the context feature vectors into that. Our wave to wake, which is also a pre-trained model, which also does the same thing from the speech is concerned. Okay, then we are taking that as a basic things, and that is where we are trying to relate to the the different context. See, each of the utterances which I was talking about, the different context which I was talking about, right, in the time context. So I was still, I told once that we are taking the larger time stamp, larger time resolution cases. So that time resolution is roughly around half a word or information it will be there. So there's nothing but when I take the chunk of those chunk of feature vectors forms the the acoustic features or the phonetic features associated to that half a word or a word level information embedded in this speech. Okay.
No, Dilip, I understand. I mean, sorry, I think
Yeah.
Professor Himamurthy has to say something.
Yeah, continuing what Shutanu is saying, I think
Yes.
I reviewed that language ID thesis at least, so I know.
Yes. Yes.
About
Right.
it. So one of the important points is we are missing is that if you look at Dravidian languages, agglutination is so common. Okay, whereas if you look at Aryan languages, Dravidian, the agglutination is not common.
Yes.
I mean, you take half a word,
Yeah.
what sense does it make in terms of the number of frames and the feature vectors for a particular language? Because when you're looking at language ID, it's the phonotactics. In fact, Shutanu, it's very interesting that I may not be able to speak Bengali,
Yeah.
but when I listen to Bengali, for example, number of times, it may not be many times even. You would immediately say, okay, this is Bengali or Odia. You may not know whether it's Bengali or Odia or
Correct.
Assamese even. In fact, I offend Odians many times telling them it's Bengali and things like that. But there is a subset that we figure out, and somehow, because it doesn't matter, Dileep, which language you take.
True.
It doesn't even matter whether you use speech recognition
Yeah.
with these models. It'll do the same thing. So it is not clear. See, earlier at least when you're doing, phone parallel language models and
Yeah.
things like that, there was language specific information that went into it. I mean,
Yeah.
that is what I think Ishtan is talking about, the stupidity of these
Yeah.
models, that it's really not. And another thing is Indian language is phrase based. We're applying the same techniques,
Yeah.
whether it is, stress time languages, phrase based languages, whatever. So, there should be some explainability
Yeah.
in all of this when we are, it's not the numbers that matter. I
Correct.
mean, 80% is still very poor, as we've already realized, for
Yes.
language ID at least. It's not good enough at all.
Yeah.
Especially when you're talking about 22 languages in the Indian context, and you have to give IDR responses in the particular languages.
Mm.
And if, let's say, it misses Bengali for ODIA number of times, it's a
Yes.
very sad state of affairs from a practical point of view. So there must be something where we put in the Bayesian framework back
Yeah.
into these models. And wave to wave has also become ancient,
Yes.
but already wave to wave there are issues with it. Yeah.
Correct.
So, and bottleneck features are one more way of looking at it. These are things I think we have to, you know, try
Yeah.
to science back in.
Yes.
Somehow the science is missing
Listen.
in
Absolutely.
all these. Shtan, it's the same story we say
Absolutely.
Yes.
just thesis,
That's the summary, actually.
in fact,
True. True. True.
you are defending a thesis, what he said. So this is the kind of thing that we are missing out on the science, and that I think, you know,
It's a dangerous trend, I think.
Yeah.
So it's a,
in fact, yeah.
It's true.
Carrying on, Chomsky says the brain is wired for language.
Yeah.
Where
absolutely.
are we making any effort to understand any of those things? It's kind of well known, but somehow these are all just put on the back burner.
Right. Yes.
So this is something I think I would like to add to what Shrutanu is saying, and it's
Right.
important for us as academicians to introspect on this.
Mm.
Very important. You know.
So Dilip, I mean, yeah, I
Yeah.
mean, I kind of completely. She has put it so nicely. I wish
Right.
that's exactly where I was trying to get. That it is not. No one has any issues with 5%, 2% improvements as long as they know exactly what
True.
they're
True.
actually. For example, I can actually cast. Even I'm saying that in language the performances are not improvements with deep learning are not as impressive as this,
Yeah.
but actually even inside speech you can craft a complex example. You can say, I mean, one example is a baby, for example, an infant, where it's doing, right? That's
True.
also a
True.
speech
True. True.
signal, right?
True.
if you look at how the mother is looking at that signal and how the father,
Yeah.
there is a great
Correct.
difference. The mother knows that whether diaper has to be changed or the kid is,
True.
that is also a classification problem, no? Whether the kid
True.
is
True. True.
hungry or whether diaper has to be changed. The mother can do the discrimination. The father can't do, and in fact, the father may get irritated because he has the next paper to write or something,
Yeah.
right? So I'm saying that the same waveform, but it's
Yeah.
actually in one case it's been getting discriminated. So what the waveform is the same, right? If I record
Yes.
it. So how can I even expect that by just looking at the waveform I'll be able to do this discrimination? It's a
Yeah.
hard problem. So essentially what we are ignoring is the role of memory.
Yeah.
So
Right.
essentially, this particular signal only gets, just like a seed, it gets germinated only when it gets the right soil. So
Yeah.
this particular waveform does not really carry in it enough information for it to even do classification, and we are attempting classification on it, right? Unless it falls on the right memory, which is actually receptive to it, right? So
Yeah.
the memory structures that are processing it so that's why there are some people who laugh at a joke, some others don't laugh at a joke, which means that
True.
just by dissecting the joke, I really cannot do language understanding. Whereas chat GPT, people think that if I give lots of text, I'll suddenly get something interesting. But what is the spirit
Yeah.
with which that text was written? And I'm saying that everything is matter. It's just
That's
gross level, right? So this understanding of the role of memory structures, this
yeah.
very complex interaction of language and memory,
True.
even if you take the theory and application of ontologies course that is being applied,
Right.
why are we doing ontologies? Because it's a rich top down knowledge of the world. Someone who has written the text actually, they can at least provide a top down picture of how the world is.
True.
We are kind of throwing all of the top down stuff away, and we are
Yeah.
saying that just by doing this analysis of text and somehow because of this, maths has become so fashionable that people don't even know how the maths originated and why people do it. Mathematicians can do the job of maths provided we know what problem we are actually solving. We don't have to really be mathematicians. I
Yeah.
was fortunate because I had a mathematician as my father, so I could get some perspective on, I had all the Russells, Bertrand Russells, and everything at my home.
Right.
So
True.
I actually am very, I at least I think I should be. I don't know. I have not done any justice to what my father was, but I should be very careful in treading the territory of a mathematician because their domain is very
True.
specific. They don't even use language. All this wave particle duality and all that has come not because the underlying mathematics is consistent, but because I carry a picture of a wave and another picture of a particle, and that's why there is a duality problem. That's the problem with language. If you use mathematical precision, there is no ambiguity. So in the world of mathematics, they don't even entertain such ideas as wave particle duality. They say, what is there? I mean, I can represent the mathematical object. Why should I care about this? So ultimately, this whole idea, this, so even entropy itself as a mathematical entity, it is beautiful. But when I say it is a measure of order, disorder, then a lot of issues come up. I can draw up an orderly picture which is actually having a lower
Right.
a higher entropy than something that is disorderly, and I
True.
can provide a counter example because this language is not reliable. The mathematical
Right.
notion is reliable,
Right.
but we are conveying false mathematics. We are conveying this baggage and not the spirit behind the mathematics, and that's why people are believing in the chat GPT story. They are not believing in the spirit behind the
It is
text,
yes.
and
True.
this wrong thing is percolating. It's as if we have gone several years back where we did not have grammar, and some children are effective in talking about language even if they have not learned grammar, and
True.
anyone can be. I mean, did people not love each other when there was no grammar? They loved. So language was meaningful even without grammar. But we have dismantled the grammatical apparatus and gone there, and now we are slowly and steadily injecting new features and writing papers to show improvements. Obviously there will be improvements, isn't it? If I take the wrong baseline which existed 300 years back where there was no grammar, and if I just take
Yeah.
large amounts of data and I keep on progressively improving my
True.
features, obviously I'll get some improvements, and that
Right.
constitutes a paper today. And we don't understand what we are doing,
What we true.
what gross injustice we are doing to this whole thing. And I wish I could have just articulated in the way Professor Hemamurthy said that where is the science behind all this.
Yeah.
And I mean, the whole classical AI, the way it blends with it, I mean, where has all of this gone? I'm so shocked at this development.
Yeah. Yeah. That's true. That I totally agree
I'm
with that.
sorry I read out myself, so because I know
Yeah.
you personally, I
Yes.
generally
Yes. Yes.
don't
I
say
no
much,
no.
but
This is Yeah,
sometimes
then,
I feel like I know the person, so I can tell a little bit
right,
more.
right,
Sorry, I mean,
no, 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 I totally
your
agree with
work
you
is
because
absolutely fabulous. I have nothing against it, but
okay.
I'm just saying you also would have faced similar things, and
No,
I
no,
think
exactly.
bring out my
Yeah,
heart.
yeah, that's true. Because with Hemamati ma'am, so we had a lot of discussions because she suggested us to do some kind of a wide works and what is the reason behind those things. So that's a nice feedback she has already given. We are just working on that. So, but it is your concern is totally agree with. Even when we discuss with the students, we also show our concern also. So, right. Yeah. Thanks for bringing
Yeah,
that
yeah.
points again.
Thanks, Dileep,
That's
for
true.
such a
Thank you.
wonderful talk, and thanks, Professor Hemamurthy, for
Yeah.
articulating it in such a nice way.
Yeah.
I actually wished I could have used some of your words.
Right. Yes. True.
Thank you.
Yeah.
It
I think
was
yeah, this is what I was saying. So because this what I was when starting. I told that like I come back as a student in this community or the IIT Madras. So because I know all of you when I was from my student time. So yeah, because I learned from you people, and then that's how carried over into the our career and all the things. They still remember all those the student days time. So
No, I think I only peripherally knew you. I never
yeah,
interacted
no,
with
it
you in
is
that
sometimes we
capacity, but
had some
we always
small.
had a relationship which was something
True,
we
true, true,
enjoyed.
true, true. Right, exactly, it's true. Yeah, really nice
I
talking
actually
to you.
don't get to attend many talks also, but it was your
Okay,
talk, and I thought maybe I'll
it's true.
just drop
It's
in and
right.
see what it is.
Okay, all right. So, okay, so yeah,
Yeah, I'm not sure whether Rupesh is here to kind of coordinate
Uh,
this.
yes, it is. I will be taking forward. Yes,
yeah.
so like, is the
Okay.
presentation done? Sir? Like, you have one slide left, I think.
What is it?
Uh,
Is the presentation done? Like, actually, you thought of
Yeah,
seeing the Alum Madras.
presentation is over. Or
No,
anything I need to share or anything to discuss, or
no, actually, thank you very much. Sir. Thank you very much for the talk, and
okay,
it's very
okay,
insightful. So, on behalf of the Rupesh sir and like Nari sir, who is also in coordination,
yeah,
thank you very much for the talk and thank you for
okay,
the time.
okay.
Uh,
Thank you. So,
thank you. Sir.
okay, Dileep. It was an
Okay.
excellent talk. Yeah, good. Very good.
Good luck, Dilip. Yeah.
okay. So thank you, ma'am. So.